Hi everyone, I'm Yifan, a PhD student from University of Bristol. The purpose of this study was to investigate the orientation effects on fatigue crack propagation of octet-truss lattice. First of all, I will introduce the background of this research. Octet-truss lattice is a typical stretching-dominated lattice. Literatures concluded that stretching-dominated lattices generally have higher specific efficiency compared to bending-dominated lattices. Therefore, stretching-dominated lattices are more suitable to be used as lightweight bearing structures, and bending-dominated lattices are more widely used in energy-absorbing applications. Fatigue failure is one of the most common failure modes of lattice structures because lattice structures in real applications are frequently subject to cyclical, mechanical, or thermal loading. For example, lattice structures are often used as hip implant, which is subject to compressive cyclic loading when people walk. Since the octet-truss lattice was proposed by Fuller, mechanical properties of octet-truss lattices have been studied extensively using theoretical and experimental methods. Modulus, strength, and fracture toughness of octet-truss lattice are highly dependent on the unit cell orientation. However, no studies have been done about the orientation effects on the fatigue crack growth of octet-truss lattice. As a lattice structure with great potential for use, it is necessary to understand the fatigue response of octet-truss lattice structures in different orientations. An experimental method has been done to study the lattice orientation effects on the fatigue crack growth of octet-truss lattice in the present work. All the lattices in different orientations are 3D printed by using photopolymer into compact tension spacemen geometry according to ASTM standard. The definition of lattice orientations and configuration of unit cell structure are shown in Figure 5. The lattice samples are defined as X, Y, and Z orientations. The orientations of octet-truss lattices were defined based on the loading direction and the local coordinates of the unit cell. For example, the load direction of orientation X lattice is parallel to the x-axis in its local coordinate. The geometry of the lattice spacemen used in this work is shown in Figure 6. The design nominal radius of the struts is 0.5 mm and the nominal length L is 5 mm. The macro dimension of CT spacemen designed to be large enough to achieve a high enough ratio of W to L in order to reduce the surface effects. All the octet-truss lattices in 3 orientations were manufactured by the SLA printing technique. Static tests were conducted first to obtain a static critical load. 2 CT specimens in each orientation were tested under displacement control at a crosshead speed of 1 mm per minute. The displacement and reaction force of the loading crosshead were recorded during the experiment. The obtained mean critical loads for orientations X, Y, and Z lattices are obtained here. After static tests, the fatigue tests were carried out under load control and fixed load ratio and frequency. The tensile load ratio R is 0.1 and the loading frequency is 2 Hz. The maximum fatigue loads are 220 Newton, 230 Newton, and 240 Newton for X, Y, and Z orientations in order to ensure the ratio of maximum fatigue load to the static critical load is between 0.4 and 0.6. This can make sure the failure time of the specimens is within one working day. The crack mouth opening displacement was measured by extensometer with 10 mm gauge length. The setup of the octet-truss lattice fatigue crack propagation test is shown in Figure 7. The typical displacement varying with cycle numbers curves or octet-truss lattices are shown in Figure 8. The displacement cycle diagram of octet-truss lattice intention fatigue test is similar to the corresponding curves of lattice under compression fatigue test, showing three-stage fatigue behavior. In the first stage, the displacement changes rapidly within a few cycles, and then displacement shows a relatively constant and minimal change in the second stage. And the final stage, the displacement increases very rapidly and specimen fails within a limited number of cycles. Photographs of the failed lattices for different orientations are shown in Figure 9. Most of the microcrack in strut initiated at the location near the joint because of the influence of local stress concentration. When the strut near the crack tip failed, the macrocrack in lattice can be considered to be extending forward, and the new strut is at the tip of the macrocrack. These struts will subsequently initiate and propagate a microcrack. The macroscopic crack propagates forwards to the critic length in such a cyclic process. Then the specimen suddenly fractured. The crack passes of orientations X and Z lattices were almost horizontal to the initial crack, while the crack path of orientation Y lattice was deviated from the initial crack by 30 degrees. The relationship between stress intensity factor range and crack growth rate can be expressed using the Pavier's law. The stress intensity factor range of CT specimen corresponding to the relative crack length can be calculated by expression from ASTM standard. Compliance method suggested by ASTM was used in this research to calculate the relative crack length during the test. The measured location and the constants CO to C5 are shown in Figure 10 and Table 1. As the clip gauge was installed and the specimen life edges, only the constants and points VO was shown in this table. The relationship between the crack length and the number of cycles for different orientations lattices is shown in Figure 11. As shown in this figure, the crack propagated fastest in orientation Y lattice. When the load ranges of different orientation lattices have similar values. The fatigue crack growth rate and SIF range were calculated according to the second method suggested in the ASTM. In second method, crack growth rate simply involves calculating the slope of the straight line relating to adjacent data points on the A versus N curve. The fatigue crack growth rates of different orientation lattices are shown here. The material properties in terms of Pavier's law are determined from this result. This figure illustrates that the fitted curves of crack growth rates of different orientations lattices were nearly horizontal. The crack in orientation Y lattice grows fastest under the same delta K. At octet-truss lattice, in Z orientation has excellent resistance to fatigue crack propagation. Here is the conclusions. The orientation effects on the fatigue properties, including crack propagation rates of octet-truss lattices, are studied in the present research. The experimental results show that the orientation has significant effects on the fatigue crack passes. The crack passes or orientations X and Z specimens are almost horizontal to the initial crack, but the crack orientation Y specimens is rotated by 30 degrees to the initial crack plane. The crack in orientation Y lattice propagates fastest under the same delta K, and orientation Z lattice has excellent resistance to fatigue crack propagation. The fitted curves of crack growth rates of different orientations lattices in log-log plot were nearly horizontal. Thank you. Do you have any questions?